So in this lesson we're going to look at two equations that I call the mirror equations. The first one is what's called the magnification equation. And magnification is really a measure of how much larger is the image than the object. It's a ratio of image height to object height. Now, we could actually derive this in class if you want. It doesn't take that much work. It's really right triangle trigonometry. And what you find is that image height over object height is also related to image distance and object distance. Now there's a negative sign in here because if the image distance is positive, a real image, you actually get inverted objects. And so the magnification is negative when the image is inverted or upside down. So the magnification equation is magnification equals negative image distance over object distance, which is equal to image height over object height. So sometimes I call this hi-ho, di-do, or di-do, hi-ho, as a way to remember which way this works. The second equation that we have is what I call the mirror equation. And the mirror equation predicts where an image is located compared to the mirror if you know the focal point and the object distance. So if you know the focal length, the object distance, and the image distance, this equation can be used to find one of those values. If a distance is negative for the image, it's behind the mirror. If your focal length is negative, the focal point is behind the mirror. It's a convex mirror. So some quick sign conventions. The first sign convention is for object location. If you have a positive object location, the object is in front of the mirror. A negative object location, the object would be behind the mirror. That'd be kind of a strange situation for an object being behind the mirror. Generally, that would be true if you're dealing with a system of either multiple mirrors or mirrors and lenses where an object of one mirror is really behind it. That's a very unusual situation. However, the next three are not all that unusual situations. An image distance being positive means the image is in front of the mirror. That means that it's a real image. If the image distance is negative, the image is behind the mirror, it's a virtual image. If the focal length is positive, the mirror is concave, the focal point is in front of the mirror, it's a converging mirror. If the focal length is negative, the mirror is convex, it's a diverging mirror, the focal length is behind the mirror. And finally, if the magnification is positive, the image is upright. That means image distance or image height is also positive. And if the magnification is negative or image height is negative, the image is inverted. So let's do a quick example problem. We're going to take a 2 centimeter tall object and place it in front 7.1 centimeters in front of a concave mirror with a radius of curvature of 10.2 centimeters. And I want to find the location and size of the image. So here are the pieces of information that I know. I know the image or the object height, the object distance, and the radius of curvature. Here are three things that I don't know. I don't know the focal length, I don't know the image height, and I don't know the image distance. Here are three relationships I can make use of. The first relationship is that the radius of curvature is twice the focal length. Second one is the mirror equation, and the third one is the magnification equation. So let's do some algebra. We can calculate the focal length of this mirror, 5.1 centimeters. Then we can calculate the image distance. And so what I've done is I've subtracted 1 over object distance is equal to image distance. And so I would then invert 1 over focal length minus 1 over object distance to get image distance. And so when I plug in my numbers, I get 18.1 centimeters as the image distance. So this is a real image. When I do the magnification equation, if I multiply by HO, I can get HI. And if I plug in my numbers, I get negative 5.1 centimeters. This means that it's both enlarged and it's also inverted. So there we've solved this problem. Now there's one thing to point out, one algebra note, and you might have seen this here with the mirror equation when I did this thing, this invert thing, and think, why did I invert that way? Why did I do it that way? There's an easy algebra mistake to make in the mirror equation, so you have to be very careful when working with that equation. The thing to remember is that 1 over f equals 1 over do plus 1 over di does not mean that f equals do plus di. Remember that if you're going to add these two fractions, you need to come up with a common denominator. So multiply the first one by di and the second one by do. And so you actually end up with something that looks like this is 1 over f. So do plus di over do di, which if you actually invert it means that f is really equal to do di over the sum of do and di. Now, we could actually do the same type of calculation for dO and dI and come up with a similar type of relationships. Yep, never mind, I had to think about that for, wait. Yes, that makes sense. I had to think about that for a second. I thought maybe I flipped the two on the bottom around, but that's not the case. So the thing to remember is that it sometimes is difficult to use the mirror equation, and sometimes it's helpful to have these three equations on there, because it's the mirror equation solved for dO, dI, and F. It's sometimes helpful to use those equations because they're a little bit more user-friendly than the mirror equation is. So that kind of wraps up our discussion of mirrors and reflection. Kind of in the next lesson, we'll start looking at lenses and refraction, and you'll actually start to see some things that look really similar in lenses and refraction with mirrors and reflection.